Hello everyone and welcome back to yet another video. This video here and the followings were recorded as deep learning introduction for students, now that no in-person training is allowed at the moment, unfortunately. So hopefully someone else out there finds them useful as well. In the first video it'll be the very basics of deep learning. In later videos there'll be content about hyperparameters, neural networks, and something about different architecture types such as convolutional neural networks and recurrent neural networks. So without further ado, let's jump on over to the presentation. So as I already mentioned, this video here will be the basic introduction to the concept of deep learning. Just on a minor note here, then the deep learning part of this course is still rather new, so we are obviously happy about any feedback you might have, corrections, suggestions, and so on. So where can we actually find deep learning today? And the answer to that is almost everywhere. So deep learning is the underlying method for most state-of-the-art applications. So for instance, speech to text recognition, which you might know from your phone or if you have some virtual assistant at home. Then in translation applications such as Google Translate, which is another area that uses deep learning. And nowadays you can even read and translate your camera input in real time. Then we have autonomous driving, which is another huge area that seems some major steps forward in the current era of deep learning. Then on your phone, you might have seen face validation, or you might have face validation on your phone. Or computer, where the system tries to automatically validate if you are the owner of the phone just by the camera input, or just from the camera input. Or it could also be face recognition, which you will see in other applications, or it could simply be on social media, where the system automatically tries to detect who the person in the photo is. So it not just tries to validate it, but actually sees a face and tries to figure out who this person is. And on a total other note, then we might have, well, more, depending on the eyes who sees, more silly or more serious tasks. For instance, if you have a pet at home and you do not know what to name your pet, then it could also be a deep learning system that has been trained to predict or give a name for your pet. So for instance, you just upload a picture of your cat, for instance, and then it predicts that this cat here looks like a Tom Glitter, or this cat here looks like a Sparky Buttons. And it can even be the other case that you don't have a pet at home. So you can also use a deep learning system to actually generate a picture, a novel picture of a pet for you. So you'll have your own little picture of a pet that no one else has. So that was a bit about where you can find deep learning today. So now let's look at the interest in deep learning, which also seems to be growing year for year. Here I just found a plot from a review paper on deep learning from Science Direct, which has an extract from the Science Direct database from 2006 until 2017. We see there is an increasing trend in the use of the word deep learning in papers. But for some reason, from 2017 at least, and in fact also later, see that the term is used less and less. And if we also look at Google Trend, how many people are searching for deep learning on Google, also see that probably over the height of people searching for deep learning. So what does this actually mean? Does this mean that deep learning is not used anymore, it's been used less? So I personally do not think this is the case. I more think that this is people not explicitly saying that they're using deep learning, and often in a paper now you would not need to write that you're using deep learning, but it implicitly you can implicitly tell in the paper that you're using deep learning, using other words, for instance, what architecture you're using, or things like that. So the deep learning era is definitely not over, and it's still very important, I'd say, knowing about what it is, what it can do, and also its limitations. So in this part of the course here, we'll first go over what neural networks are and what deep learning is, and then on how we can improve these deep neural networks using hyperparameter tuning, regularization, optimization. Then we'll have something about convolutional neural networks, which are often used to analyze images. And there also go over some popular architectures of convolutional neural networks. Then in the end, we'll have a video about sequence models, just briefly touch upon that topic, and afterward also beyond the basics, so other things that deep learning is also used for. But in this video here, we'll just talk about the basic, namely neural networks and deep learning. So at first, there'll be a bit more motivation, why we see this increase in usage of deep learning, then how we can formulate deep learning, these systems as a computational graph, then something about artificial neurons, so an artificial neural network, which is also often called. So what are these artificial neurons? Then something about forward propagation, the different activation functions that you will find in a deep neural network, how back propagation works, different loss functions that you will use to optimize your system. Then briefly about the long-running history of deep learning, how far it runs back. And finally, something about the different deep learning frameworks that you might encounter. And here's just a list of links to different literature out there. So there's neural networks and deep learning, which is a very practical book with a lot of code and very little, I'd say, mathematical notation. Then on the opposite side, there's the deep learning book, deeplearning.org, which goes all the way from introducing linear algebra and other machine learning techniques, which is also useful to grasp the full understanding of deep learning. Then there's another very nice course from MIT, which is also very practical and in lecture format, this Intro to Deep Learning. Then from Coursera, there's a MOOC, a whole specialization, in fact, on deep learning, where it's in this MOOC format, so very short videos about single topics at a time. But this here is just a short list. There is literally like an endless amount of material out there on deep learning. So what is deep learning? So I found this overview here from Introduction to Deep Learning, where we have as the overall topic, we have artificial intelligence, which is just any technique that enables computers to mimic human behavior. Then as a subset of that, we have machine learning and pattern recognition, which is the ability to learn without explicitly being programmed to do so. And here, the difference between machine learning and pattern recognition is essentially just that pattern recognition has its origin in engineering, whereas machine learning grew out of computer science. But they are essentially two facets of the same field. And then as a subfield to machine learning and pattern recognition, we have deep learning, which is just the way we extract these patterns from our data. And deep learning then uses neural networks to extract these patterns from our data. So why do we see this increase of the uses of deep learning? So there's essentially three parts to that. So big data, hardware, and software. So we'll have a bit more look at the ImageNet, for instance, which is an example of a huge data set. which has been made publicly available. So a huge data set annotated for people to directly use and train their system upon. Then it has been easier to collect data and store data, especially from the increased usage of social networks. Then from the hardware side, we also see that graphic cards become more and more powerful, and people found ways to put some of these algorithms onto the graphic cards instead of executing the algorithms on the CPU. And this makes it possible to have an enormous parallelization of the algorithms. And last but not least, something about software. So instead of everyone implementing their own deep learning systems, then there is these open source toolboxes which has made it very, very easy to train deep learning systems. So you don't really need to know how it's actually working on the hood. You just need to know more or less how to provide input to a system and what output to provide. Besides just the open source toolboxes, then there's also a lot of open source and pre-trained models out there. So even though you do not have the hardware to train a lot of large models, then there's people who already train models. So like all the pre-trained weights from some larger networks, they'll be publicly available for you to download and use. So you can directly download the model, download all the pre-trained weights, and use the system directly. So for instance, you can just download the model and the weights for a system that will classify an image. Then it'll take an image, and then it'll tell on the output, for instance, if the image contains dog or a cat or a banana or whatever is found in the image. So why is deep learning, why does it seem to take off compared to some of the other algorithms? So as such, it just comes down to the amount of data. Whereas older algorithms, they seem to stagnate after a certain amount of data, then they do not really improve anymore. But deep learning systems, you can just continue adding parameters in a very easy way, just by adding, like making the models deeper and deeper, adding more parameters, and also adding more data. So you just add more data that the system can train on, make your function essentially larger, and it will increase performance of your system. And then we see that small and medium-sized companies, they have already access, to a lot of public available data, can still train systems that way outperform some older algorithms, more like simpler systems like logistic regression maybe, or support vector machines. And then we see the industry giants, they really have access to a lot of data, so they can make these systems as large as they want, and they can just continue feeding it with data and continue improving performance. So regarding the availability of data, then one example of a big data set is ImageNet. And later on we'll hear a lot about other nets, such as LeNet, AlexNet, and ResNet. The thing here to remember is that ImageNet is a data set, whereas literally all the other nets you will hear about, like LeNet, AlexNet, ResNet, and so on, they refer to the configuration of neurons in a network. So ImageNet refers to this huge data set. There is 14 million images divided into 21,000 categories. And one example of such a category is, for instance, banana. And if you look inside ImageNet here, then you'll find 1,409 pictures of bananas. So as you see, just a small example here. Then there's zoom in pictures where it's really, really close up. You see the full banana, you see parts, some of them where it's peeled, half peeled. You see some of them where a person might have taken a bite of it. Multiple bananas in the same image. So the variety of images of bananas is really, really broad. And together with ImageNet dataset, there are also have a classification task, and the task here is to produce a list of object categories presented in an image from 1,000 categories. And usually they will evaluate this here on the top 5 error, so the rate at which the model does not output the correct label in top 5 predictions. So one reason why top 1 error is very difficult is the way that the classes are constructed. So take for instance the class of dogs. The dog is, so instead of having an image in the data set and then the ground truth label being dog, instead you will have the type of dog. So you will have to not only classify it as a dog, but you'll have to classify that this is a Maltese, Terrier, Bulldog, Great Dane, or any other kind of dog. So you might not get it right that it's the what type of dog it is, but you might get it right that it is some kind of dog. But the way that the categories they're structured, then it at least makes it possible here with the top 5 error to get a very decent performance. Then if we look at how some of the people taking place in this on this scoreboard of ImageNet, they're performing, then literally before 2012, it was not deep learning methods, and then from 2012 and forward, it has been only deep learning methods, which was kicked off with AlexNet in 2012, which was the first convolutional neural network to win. So again, we'll talk about convolutional neural networks later. And then from there, it is just the performance has just dropped, and even you see in 2015 with ResNet, a network consisting of 152 different layers, got below even what we would consider as humanly achievable. So if a human was giving all of these images of different, like a dog or a cat or so on, they would also have to specify the correct type of dog and cat. And here people have measured that humans have an error of approximately 5.1%. So the majority we'll be talking about in this course here is simple classification, which makes it very easy, at least to begin with, to explain the deep learning system. If we want to do more than that, simply just have to do a lot of additional tricks. But we'll also go over how, for instance, to do localization of the object in your image. So we can just have at first look at single objects, classifying an image. Here's an image, classify what it is. The second level would then be, okay, where in the image do you find this object? The next level would then be finding multiple objects in your scene, in your image, and kind of on the very difficult level is instance segmentation. So really find a tight segmentation of each of the individual objects in your scene. So you might often have heard people talk about this magical black box. Essentially, you put in something, it could be an image, and then it, by magic, outputs what it is. For instance, an image of a cat. Then it puts out, okay, this is 97% a cat I've seen this image. But we do not really know why, or what features of the image it actually looks at to classify this as a cat. So in more recent time, there is papers that are looked at, for instance, some heat map. So along with the classification of this as a cat, then it can also tell you what features of the image were important for the network classifying this as a cat. But by a lot of people, it is simply seen as this big system where you just pour in a lot of data. Then there is some matrix multiplication, and you collect the enter on the other side. And if it doesn't work to begin with, then you just add more data or stir around the data a bit until you get the answer that you're actually looking for. And this can also feel a lot like this to begin with, but when you get into it, then you'll see that there's actually a lot more to it, and you'll learn that there's a lot of knobs that you can can tune your network to produce the output that you're actually looking for. So what is a deep neural network? So an artificial neural network consists of simple elements called neurons. And a neuron can make a simple mathematical decision. And then by combining all of these neurons, we can analyze complex problems. And here we have an example of what will be considered as a shallow artificial neural network. It's not a deep network. And the reason for this is that we have here one input. So this here could be an image, and an output here where we would have our, for instance, the class. Is this here a cat? How likely is this to be a cat? How likely is this to be a dog? And so on. And then we just have one hidden layer. So as soon as we have more than this one hidden layer in our artificial neural network, then it will be considered a deep artificial neural network, or a bit shortened for deep neural network. So here we see that we have not 1, 2, but 3 hidden layers. So as soon as we have 2 or more, then it's a deep neural network. And then we have also with the network, which also applies for the shallow network, but we often refer here to the forward and the backward direction. So a forward pass is that we put in, for instance, our image here, we compute our output, and then there might be some error, at least in the training phase, regarding this input. So it might be an image of a cat, and here then it might not fully classify this as a cat. So this, we compute an error, how wrong the network is, and then we back propagate in our network to figure out how much we adjust each weight, such that we will eventually produce a correct result, which would, for the given image, be cat. So we have these deep neural networks, which is just a network of neurons. So how are these networks actually constructed? So they are constructed in a computational graph. And a computational graph is a directed graph where the nodes correspond to operations or variables. So variables, they can feed their value into operations, and operation can feed their output into other operations. And in this way here, every node in the graph defines a function of the variables. So here on the left, we just have a directed graph, and on the right here, a computational graph. Now let's look at how we can turn a function into a computational graph. So the challenge here, or the idea here, is we want to graphically visualize the computation of a function using a directed graph. And here's an example. The goal is to compute the function j. And then we want to look at how to compute the function output, and afterward then how to compute the gradient, the partial derivative of this output, which we'll then be using later on. But for this example, let's open up a whiteboard and then do the calculations there. Okay, so let's first try to write up what the task here actually is. So we have the function j, a, b, c, which is equal to 3a plus bc. And now the idea is to write this up as a directed graph. So let's start out with 3 input nodes. And call this A, B, and C. And now the first operation we could do is B multiplied by C. Let's put this into another intermediate variable called U. So we'll have U equal to B times C. Then we feed B and C into this node here. Then the next part will be A plus U, which we can then make another variable called V. So we'll have V equal to a plus u. So this node here can go up there, and this one. And then finally, then we will have j, then we can compute the output of j, which is then equal to 3 times v. So now let's try to add some values to our variables here. So let's say that a is 5, b is 3, c is 2. So now we can compute u will be 6, and 6 plus 5 here will be 11, and the output will be 33. Okay, so far so good. So maybe for this small example, it's not too interesting to compute the partial derivatives, but I think this example here is small enough and makes it easy enough to see the full computations and kind of grasp the full concept. So the partial derivatives, so essentially what happens to the output if we change one variable and keep everything else fixed. So let's have a look at what happens if we change 5 here and increase that to maybe 5.001. So this here is also what is known as, well, partial derivative of j with respect to a. So one way we can compute this is by looking here at a. Okay, we increase it to 5.001. What would then happen with v? V would also increase to 11.001, and then eventually j, our output here, will also increase to 33.003. So we see here that by increasing it 0.001, the output will increase 0.003, which means that we have the partial derivative of j with respect to a is equal to 3. That's a 3 times impact on the output if we increase this this variable here. And now we can do the same for b and c and u and v, and kind of forward propagate this through the network. But what you might see here is that there's a lot of redundant computations. So an efficient way to do this instead is using what is called backpropagation. So compute the gradients in a backward manner. So one concept we'll need to use here is the chain rule. So if we have our output, let's just try to write 3 small nodes down here. So if you have our output j, and we have our input a, and there is some intermediate variable b here, then what we're interested in is the partial derivative of j with respect to a. But this is also equal to partial derivative of j with respect to b, and the partial derivative of b with respect to a. So we can kind of divide it, and instead of computing the full partial derivative of the full network, then we can divide it up in steps. And this here is what is known as the chain rule. And remember not to confuse this chain rule here with the chain rule of probabilities. So how does this now work? So let's try to first find the partial derivative of v here on the output. So if we find of v, so what is derivative of j with respect to v? So here on the output function, what happens if we take the gradient here? So just removing v, so partial derivative with respect to v is 3. So now we can look at the variable before that, namely u. So what is the partial derivative? Maybe we write that down here. Derivative of j with respect to u. So this here we can then split up and say that, okay, now we already have the partial derivative of v, and then we can then take the partial derivative of v with respect to u. So we already computed the first part here, as you saw, which is 3, and partial derivative of v, so this equation up here with respect to u. So this here cancels out, and u, this is 1u, so this one cancels out, so this is just 3 times 1, so 3. And now we could then backpropagate one more time, and then take partial derivative of j with respect to c, for instance, which would then be exactly what we had before, v over u, and u over c. So we already have the two first parts here, this part here and this part here computed. So 3 times 1 times partial derivative of u with respect to c. So that is cancelling out c, so that's just b, and b is 3. So this here will just be 9. So what you see here is that we are just following backward here in the graph this way here. So going forward, compute the output, going backward, computing the gradients of partial derivatives of all our variables in the graph. So the last one we need here is b, and the only thing we need to look at here is just change out this last part here. So instead of u with respect to c, then it'll be u with respect to b, which would then be cancel out b instead of c. So we'll just have 3 times 1 times 2 for, which will then eventually be 6, for the partial derivative of j with respect to b. Okay, so I hope that gave you some intuition about how to do both the forward pass of a deep neural network in such a computational graph, and also do the backward pass, so computing the partial derivatives of all the variables in our network with respect to some output. And in this case here we have the output j. We'll see later on how this j here can be formulated. So now let's look at how we can easily represent, for instance, linear regression in a computational graph. So here we're just working with a simple 1D example. So we have our output, which is the mean squared loss. So suddenly we do not have the j function on the output, we just have the mean squared loss here on the output. Then we have one input variable x, we have our weight here, and we have our bias term, which then in one node here is we use to compute the output of our function here. This here is one way to represent the computational graph, but in neural networks, what we often do. So an alternative way to configure our graph is now to, instead of having a node for our weight, remove that and put the weight on the edge between the nodes. And the same for the bias term, we'll add a node with a 1, and then the bias term will be the weight as such here on the edge between the one node and our computation node in here, which will compute our output y hat. So this here is just a small simplification of the classical computational graph, which makes it easier to get an overview in a much larger system with many more nodes. And what we can now do is compute the partial derivative of the output with respect to the loss function here. And then we can also compute the partial derivative here of the output y with respect to x, what that is. And then we can get a idea of the partial derivative of the loss function with respect to our W parameters. So usually in linear regression, what we are looking for is how to optimize the parameters W and B. So here is just the form for how to update W. And yeah, then you could do the same for updating B, at least find the partial derivative of the loss function with respect to these variables, and then we can use, for instance, gradient descent to optimize these variables. Another algorithm which we can also easily represent in a computational graph is, for instance, logistic regression. So here, just increase it to 2D. So now we'll have x1 and x2, and again we'll just have a one node which represents our bias term. Then we can do a simple vector multiplication by our W, which is now a 2D vector, multiplied by x, which is also 2D, plus b. Then we can look at our at another node, which is then just our sigmoid function, which squashes our c into the range 0 to 1. And then finally, we can have the final node, which is our loss function of our network, which in this case here will be a binary cross entropy, so the function mentioned here. And just like in linear regression, now we can then do the back propagation to figure out the partial derivatives of W1, W2 with respect to the output, and for instance use gradient descent to optimize our logistic regression classifier. So very rarely when you hear about deep neural networks, you'll hear about computational graph, but you'll hear about the architecture of the network, which is essentially how these neurons are structured. But the architecture can often be described or written a bit differently. So neural networks are organized into groups of units called layers. So we'll have different layers of the network. And most neural network architectures arrange these layers in some chain structure. So then we'll have layer 1, layer 2, layer 3, and so on. And yeah, each layer precedes the other ones. There are, of course, different architectures that does not use this structure. We'll also go over some of those. But this here is especially for fully connected neural networks. So multi-layer networks are often preferable over 3-layer networks because they usually generalize better. So here is then an example of a neural network, which we also saw on a previous slide, where we have the input, the output layer, and then 3 hidden units. And how we can then compute the output of the first hidden layer here. So this here, H1, is the output here after the first hidden layer, which is a simple matrix multiplication, so which is why we want everything to be fully connected, therefore the name, the fully connected neural network. So every single neuron here, this neuron input, is connected to every single neuron here in the first hidden layer. And the same goes for this neuron here up here, is also connected to every single neuron in the second hidden layer. This makes it now possible to do some very simple matrix multiplication. So we just have a big W matrix times our input vector, and then plus some bias term. So in this graph here, we have not mentioned the bias term is not shown, so we can add that manually down here. We'll just have one neuron with 1, and then from there there'll be an edge to each of the nodes, and on each of these edges, there'll be bias 0, and then this here bias 1, and so on. And then the output of layer 2, so over here, there'll just be a matrix multiplication of all the weights we have in here, times all the outputs of the first hidden layer here. And then again, we'll have another bias node here, or one node, and then all these bias weights here. So the bias term is always it's 1 and shared among all the neurons in the network, but it's often left out in architectural visualizations. And now we can easily have a look at what is the number of parameters in this full connected network, where in 1 it's just the number of inputs here in our input layer times h1, which is the number of neurons here in our first hidden layer, then plus h1, because we have the bias terms we also have to remember to compute. Then h1 times h2 is just the number of neurons in the first hidden layer times the number of layers in the second hidden layer, which will then be how many weights you'll have here in between. Then plus h2, because we have to remember our bias term. Then again, all the weights here between second and third, the bias, then the weights between this third hidden layer and output, and finally there might also be some weights or some bias term here for the output layer. So far we talked a bit about backpropagation, or in short backprop, which just refers to the process of backpropagating the error through a computational graph to compute this to compute the gradients of the network. Then we have the algorithm gradient descent, which is an iterative optimization algorithm to find the minimum of a function. So this algorithm just takes steps proportional to the negative of the size of the gradient, and then by iterating, you will eventually end up in a local minima. But quite often, in fact, the backprop is used also to talk about the optimization process. So backprop sometimes wrongly also refers to both computing the gradients and take a step in the negative direction of the gradient. So the simple gradient descent is just we have your current parameters, wt, and then you take the gradient a step lambda in the negative direction of the gradient, and then you loop that until the weight doesn't update more or less anymore, and then you say you converged and then return your final w parameters. So here we have a graphical example of how this optimization process looks like, where we just take small steps in opposite directions of the gradients and eventually converge to some kind of local optima, for instance, down here. So what you might note is that the algorithm is quite sensitive to the initialization of the parameters. So you might initialize here, but if we initialized over here, for instance, then we might end up in a local minima down here, or it could even be that we would end up in a local minima down here in case that we initialized over here or something. So a good idea when using gradient descent optimization is always to train your network multiple times by randomly initializing the weight of the network. So a deep neural network consists of a lot of different neurons. So on this slide here, we'll just look at how are these neurons actually, what does these neurons actually do? And how can we model these neurons? And usually for modeling these, we can use a simple perceptron. We'll look at later how this can be slightly more advanced than just a simple perceptron. And a perceptron here is also referred to as an artificial neuron, which kind of tries to highlight the original inspiration from biological neurons. But what's going on in a neuron is that we have our input, for instance, x0, x1, x2 out here. It goes in, so x1 is multiplied by, or x2 here is multiplied by 4, x1 is multiplied by 0.6, x0 is multiplied by 0.7. So these weights here are all the ways that we are usually trying to optimize in our network. So after we did this multiplication, then we sum the outputs of these multiplications, and then we make a simple threshold. So we see if the multiplication of the input with our weights plus some bias term is below or above or below 0, and then either we'll turn the output of the neuron 1 or have it to a 0, or maybe a -1. So it depends a bit on the configuration of your neuron. So maybe also just on a note here is that a neural network, a feed-forward network, is a function approximation machine that is just designed to achieve statistical generalization, which occasionally draws some insight from what we know about the brain. So what is important here to know is that neural networks are not modeling how the brain works, but it's more, it occasionally draws some insights from how the brain works, which makes quite a difference. And you'll often hear people talking about that neural networks, or AI systems as they will also refer, they're doing exactly like, or they're modeling what the brain is doing, and this is simply not correct. So in such a neural network, I'll just try to set up a small example here of what the neurons inside the neural network might learn. So here is a small thought of example. So we have some inputs to our network, so all our variables. So it could be that there's a variable that is number of lectures a student attended, if the student is a cat owner, number of exercise points you gained from doing the exercises of this course, the current weather outside, if you speak Danish, if you took a SAT score, then what your SAT score is, if you're good at, and also how you performed in your linear algebra exam. Then let's say we have a neuron here, which might end up, so this is definitely not for sure, but this neuron might end up learning something about if the student is following the course. And then hopefully at least it figures out that, okay, W1 here, number of lectures the student attended, hopefully that is important to figure out if you followed the course. Maybe also a number of exercise points here. And most of the others will probably be less of importance. And there could be another, so essentially this weight here could be quite high, and everything else could be more or less close to 0, like if your cat owner probably doesn't have much influence on if you're following the course. The same with how the current weather is outside. This weight here will probably also be close to 0. Then we can add another neuron in our network, which might end up modeling something about if the person or the student is generally smart, which might not be correlated with number of lectures attended. So in fact, for this neuron here, the W1 might be close to 0, or at least a very low value. Whereas if how well you performed on your SAT score here, this parameter here might be higher, and the same with maybe how well you performed in another exam. This might also be quite important. Then we can then feed these neurons into another neuron, which will eventually give us a pass-fail of this student. So then we can optimize over a data set maybe of previous year students, figuring out what is the actual parameters of this network. And then we can test on students from this year, for instance, or keep out a test set from students from last year and try to see how well does our system actually perform. Is it able to predict how, like if a student will pass the pattern recognition exam? So there is in fact one big problem with this step function which we looked at so far. In fact, two problems. One is that it's not differentiable at 0, and the other one is that it is zero derivative everywhere else. So here at 0, when you have such a step here, it's not well defined how the gradient is at this point. And if we just have a flat function, what is the gradient here? It's just 0. And if you remember from gradient descent, the idea is exactly to use the gradients to adjust our parameters. But now our parameters, or the gradient here, is 0. So the gradient will not give us any information about the direction to go. So how much we should adjust each of our parameters in our network. So maybe this step function here is not the best function to use in our neurons. So what we can use instead? Is, for instance, a linear function, which is differentiable everywhere. But the linear function also has some problems. For instance, it can only model linear functions. So what is the problem with only modeling linear functions? So here we have a small data set, and the task here is to have some decision boundary that would classify a new point if it belongs to class green or red. And if we just have a single linear function, then it's at least very difficult to get a decision line that would capture this data correctly. So in order to be able to estimate this decision surface here, we'll have to rely on some nonlinearity. Find some nonlinear functions in our to add to our system. So one activation function we could use to add some nonlinearity into a system is the sigmoid function, which you might know from logistic regression. So this function here maps the input into the range 0 to 1. So the blue here is the sigmoid function. And see, no matter what input, then it'll just map it either to 0 or 1 or some value in between here on the slope. And then we can decide here how steep this slope is. So there's a problem here, which is it reduces the gradient for large inputs. So if you have very large inputs, so if the input is very large, for instance over here, or very small over here, then we also see that the gradient here is close to 0, or close to 0 up here, which again means that we would not be able to learn anything in case that our gradients are so small. So with n layers and n small derivatives, we multiply all of these small derivatives together, and the gradients decreases exponentially backward through the layers. So the more layers we add, the bigger problem it becomes to use the sigmoid function. So very small gradients, weights and biases will not be able to be updated in our network using gradient descent. So another very popular function is ReLU. So the ReLU function is very simple, rectified linear unit. It's very efficient to compute, and there is a way smaller risk of vanishing gradients. So here we see the function. So it just clips everything below 0 to 0. So it's very simple in that regard. And if we look at the gradient, then the gradient is as simple. So it's in fact a step function, the gradient here, which is just 1 above x and 0 below. So one thing you might see here is that it's not differentiable at 0, but in practice, in fact, this does not show up as a problem. And using this ReLU, people have shown that this has a lot smaller risk of these vanishing gradients. So if you have very, very deep networks, vanishing gradients, this means that, yeah, the gradient goes to 0. Eventually, like the further back you propagate throughout your network. On this slide here, we just have a small example of different activation functions. So we already went over the linear activation function. Then there's this binary step function, which we also went over. The logistic regression, or the sigmoid, function, then as an extension to the sigmoid, there's also tanh, which performs slightly better. So instead of squashing the function or value into 0 to 1, then it squashes it between -1 and 1. Then we have the ReLU, the rectified linear unit. And as an extension to rectified linear unit, there is the leaker ReLU, which instead of cutting off all the values below x, then just sets all the, or multiply all the values by a very small amount, so 0.001. And the same for the gradient, which would then just be 0.001 for x below below 0 and 1 for everything above. And then again, as an extension to this, you can also have the parametric ReLU, where you can specify yourself this alpha parameter, which would specify exactly how much or how large your function will be below 0. Then I just included here a link to an online training app where I would encourage you to go in and try this out. So what you can do here is load a simple toy example, for instance the XOR problem here, and try to optimize your parameters of your neural network, either using linear activation functions or different nonlinear activation functions, and then you can get a grasp of how the decision surfaces look like. You can also add more neurons or less neurons to your network to see how it performs. So now we come to another very important part of deep neural networks, which is loss functions. So how to quantify how wrong your network actually is, and use this knowledge to optimize your parameters in your network. So how to quantify loss? So the loss of a neural network measures the cost incurred from an incorrect prediction, and measuring this error on a single training example. So usually the loss function L here just predicts or looks at giving a single input X. So this could be an image, for instance. What does the network predict as the output, and what should it have predicted? So in this case here, for instance, that it predicts 0.1 on the output, and it should have predicted 1. Now you can specify your loss functions, like different loss functions for different scenarios. For instance, you already saw how to do it for linear regression and logistic regression, what the loss functions will be there. As an extension to the loss function, then we often also describe the empirical loss, where the empirical loss here is the measure of the total loss over the entire dataset, which usually captures somehow the mean of the losses. And this empirical loss here is also often referred to as the objective function, or the cost function, or the empirical risk. So given 3 inputs here, 1, 2, then you'll also have what the output of network, what it outputs, and what it should have been. Now you just sum over all of these outputs here, so sum over your loss function for all of these predictions to compute the empirical loss. So instead of just having one input and compute the loss, then you would usually put in, if not your full data set, then at least what is called a batch, so parts of your data set, and compute your empirical loss on that. So a very popular loss function early on, maybe in the 90s at least, is the mean squared loss, which just takes the square difference between your true label and your predicted label, and then average over your full data set. So as an extension to the mean square loss, what we can use is the binary cross-entropy loss, which is also what was used in logistic regression. And this can be used with models that output a probability between 0 and 1. So like either probability 1, this is true, or probability 0, this is not true, when it's belonging to class or not. So it could be a simple binary classification of an image. Is this a cat or is this not a cat? There'll be close to 1 if it is a cat and close to 0 if it's not a cat in the image. Or at least that's the idea, that this is what the model should output. For instance, we can see here that then the model here outputted 0.3, but it should have been 1. And here it outputs 0, and it should be 0, so this here is correct. So this here will count less in the final or the total computation down here of the loss function. And then there's the third example here, 0.8, which should have been 1. So as an extension to binary cross-entropy, there is what is called categorical cross-entropy loss. And this here is also often referred to as softmax loss, which consists of a softmax activation plus the cross-entropy loss. And this here can be used to output the probability over k classes. This just is seen in ImageNet, where you had, what we saw in the introduction, that there were 1,000 classes. Then with softmax function here, we'll output a probability for each of these classes, and we'll then normalize it such that the sum of all the probabilities of all these 1,000 outputs, they'll equal to 1. So here is just a more graphical example, plus with the total empirical loss down here mentioned for the categorical cross-entropy loss. And what we see here is that each output for all the 3 outputs here should then equal to 1. So 0.5 plus 0.3 plus 0.2. And the same with this row here should also equal 1, and this row here should also equal 1. But then in your actual data set, what you are then comparing to is that the output here should have been 1. So maybe this one here is exactly what is outputting if the image is a cat, for instance. Then this here, as we see from the ground truth, this should be 1, but it only predicted that the output is 0.3, so 30% certain of this being a cat, and maybe it's 50% sure of this being some other class. So nowadays there's a lot of different open source frameworks to do all the forward and back propagation automatically for you. But it might also be quite good to know how these frameworks, what kind of computation they're actually doing, and what kind of values they have to store, just to get a notion of the memory requirements for your system, and why suddenly it says out of memory. But also if you had to, or if you want to implement it yourself, then at least some tricks to remember here. So if you have your input x, some data, what you will then be computing is your some intermediate variable c, which is just your multiplication of all your weights in the input times the input x, so your input data, plus some bias term. So you store this in this variable c before you put it through the activation function, which in this case here is a ReLU activation function, and then eventually compute the output from the first hidden layer. Then you put it into the second hidden layer. Again, you multiply the output of the first hidden layer with all the weights plus the bias terms, and store this in the intermediate variable c2. And then you compute the output. In this case here is just a simple sigmoid function. So we'll just have a single output between 0 and 1. And then you would compute this output over multiple inputs. So x is not a vector, but maybe a full matrix instead. So you can compute your empirical loss of the network instead. And then when you do the backpropagation, what you in fact need is this C variables. So this is why it's quite important to store this intermediate result, such that you can compute your partial derivatives of your loss with respect to the weights and the bias. You can backpropagate again, and also make use of this intermediately stored variable C, backpropagate again, compute your gradient of the loss with respect to all the weights in the first layer, and you can in fact also compute the gradients of the input, or with respect to the input, which can be useful in some applications. So what you see here is some intuition about deep learning networks and then what they actually represent. So I think this here is maybe more representative for convolutional neural networks, but they are also part of this whole family of deep learning. So the idea is that some of the first layers, they will learn some very simple features, for instance, edges. Then in later layers, you would have, for instance, eyes and nose and mouth and so on. And in later layers again, you would have maybe full faces, which is then a combination of different eyes, mouth, nose, and ear. And then on the output, either it could just be a simple validation. Is this person on the input equal to some person that you trained the network upon? Then it'll be a simple probability value, something between 0 and 1. Or it could be that you're trying to figure out this person, who it is, from a library of millions of different faces. That could also be a possibility. But just some intuition about that. Usually the deep neural networks, they try in the beginning to find some very simple features and then add upon these, which is why you have this deep representations instead of very wide networks. So when talking about deep neural networks, also important to note is the universal approximation theorem. So what this theorem is telling is that a feed-forward network with a single hidden layer containing a finite number of neurons can approximate any function, but the layer may be unfeasibly large and may fail to learn and generalize correctly. But by using deeper models, this can reduce the number of units required to represent the function and reduce the generalization error. This is some findings from the neural networks and deep learning from Michael Nielsen, where he had an intuitive discussion on the topic. Okay, just before ending this video here, I'll just quickly go over some of the history of deep learning, just to show you that in fact it's not that new what we're working with here. So modern feed-forward networks is the accumulation of essentially centuries of progress. So back in the 17th century, this chain rule that we saw earlier that analyzed the backpropagation algorithm was invented. Then in the 19th century, this way of iteratively approximating the solution was invented. In 1940, the linear perception was invented. Then in 1965, we had the multilayer perception. In 1989, the first versions on convolutional neural networks were introduced in form of LINET, which showed its uses on handwritten character recognition, and they used the Sigmoid activation functions all over. Then in 2006, kind of the deep learning renaissance started due to datasets, and suddenly our computation power had become much, much larger. In 2009, the ImageNet dataset was introduced, and in 2012, the first deep learning system to win this ImageNet challenge was published. So the core ideas behind modern feed-forward networks have not changed substantially since the 1980s. The same backpropagation algorithm and the same approaches to gradient descent are still in use. But what we'll see later on is that instead of the simple backpropagation, there's a lot of new tricks to use to both train deeper networks and train them faster and train them more robustly. So also most improvements in neural network performance from the 1918s to 2015s can be contributed to two factors. Just as a recap here. So one, larger datasets, which reduces the degree to which statistical generalization is a challenge for these networks. And secondly, larger architectures due to more powerful computers and better software infrastructures. And what is additionally important in some algorithm changes here is the simple replacement of the mean squared error, which was popular between the 1980s and the 1990s, with the simple cross-entropy loss function known from the logistic regression. And then also replacement of the sigmoid activation function in hidden units with this piecewise linear hidden units such as ReLU, which has made it much faster to compute all the outputs of these activation functions. Then on a very small note here, there's just a lot of different deep learning APIs out there. And nowadays, it doesn't really matter that much which one you are starting with. I'll probably advise either PyTorch or TensorFlow, but essentially all of them, they provide some high-level API for learning neural networks, where you can easily define models, load data, automatically differentiate your functions. Most of these libraries are implemented in Python, and some also in C++. As a summary of this video here, then we have a deep neural network is represented or can be represented as a computational graph, which is what is usually done. And each of these artificial neurons can be modeled as a perceptron, where we slightly modify this activation function on the output. So the choice of this activation function is important to be differentiable, and small derivatives should be avoided, which can lead to these vanishing gradients. We'll also be looking at this later on. And there exists a ton of different cost functions depending on what your system is optimizing for. But the most used one, I would say, is probably cross-entropy for classification tasks. With deep learning libraries, as mentioned here in the end, we only need to specify essentially the forward path, and then the full backward path, which went over, is automatically handled for us. And just in the last slide here, again, links to different some materials, some online books, other online courses about deep learning, and also some GitHub repositories and websites where quite a lot of the material here is from.